So in this video, I'm going to be going over a basic implementation of the binary search tree in Java, and talk a little bit about what is a binary search tree and why is it a little bit more efficient and why we should use it. So a binary search tree is really similar to a regular binary tree. It holds the same functionality. The parent has up to 2 children and so on. The topmost parent is called the root. Everything has leaves or internal nodes. But the interesting part about a binary search tree is that it's ordered. This means that the parent's left child will always be smaller than the parent, and the parent's right child will always be bigger than the parent. This allows for because it's sorted, it allows for really good searching abilities, and makes it a lot more efficient. So again, just like our binary tree, I have a private class tree node within my binary search tree. It's your usual tree node. It has a parent pointer, left child pointer, right child pointer, and the data for the actual node, and 2 constructors, one that takes in the data and the parent, and one that just takes in the data. So then up here for my actual class, I have my root and my size, and then the basic constructor, it's your default constructor, function that returns the size, an iterator, and is empty. And then we have our insert function. So our insert function takes in an item. It creates a new node with that item. If it's empty, the root will just automatically point to the new node, or it will call the insert helper function. So the insert helper function takes in a node and the node to be added. So originally we called this function with the root. So we have the root and we have a new node, and we're going to check to see if the new node fits under it. If it doesn't, we're going to recursively call it with the node next to be checked and see if it fits under one of those. So to do so, we check if the current node is greater than the node to be added. If it is, it will check if the left is not null. And if it isn't null, then we recursively call it, because we can go further down and you can add it to a different spot. But if it is null, then we just add it into the spot because that's the order and that's where it should go. So otherwise, if the current is less than or equal to the node to be added, it will check the right child and recursively call itself to compare again, or if the right child is null, it'll just add itself in. So that's how you insert a node into a binary search tree. And for deleting a node, this function will take in the item to be deleted. What I do first is we make a new node, and we search for that item. The search function we will go over in a little bit, but basically it returns a node containing the item passed in. So now that we have the node with the item, if that node is not null, so that means if the item is truly in the function, we will call the delete helper on that node and decrement the size. So the delete helper takes in the node to be deleted. There's 3 cases and it will delete the node accordingly. First case, if it's a leaf. If it's a leaf, it's a simple deletion. It'll just remove itself. If the node to be deleted has 1 child, it removes the node that has to be deleted and then adjust the children accordingly. But if the node has 2 children, you need to find the in-order successor, replace the data, and call delete all the successor. So what this means is it'll basically look for the next number that can fill that spot, and then it'll fill the spot, and then you have to recursively call this entire function with the successor because that just got deleted itself. So here it's basic node pointing and pointer manipulation. Here again, we're just removing and adjusting children, and here we just recursively call it. And then this is my successor helper function. It takes in a node and it will return the it takes in the right child of the node you're looking for. So you pass in the right child of the node you want the successor for, and it will return the successor, the in-order successor. Just to make it a little easier, by passing the right child, that means you can go all the way left until you can't anymore, and then just return that node, because that's what it means to find the in-order successor. So, and then next I have my find function. This will return true if the passed item is in the tree and false if not. It'll call search, which we will go over in a second, with the root and the item. If the node returned is null, that means it's not in the tree, and if it's not null, then it will return true because it is in the tree. So the search function, as we've talked about a little bit before, it takes in a node and an item. It will take that node, and we usually pass in the root, and it'll trace down the whole tree and try to find that item. So if the current node is the item, you just return the node because that's your base case. If the item is smaller, you want to check the left side of the tree. So you go in and again, you check if the left child isn't null because you can't call something and it's null, and you recursively call the function again. If the item is greater than the current node, we're going to check the right side. So we go down the right side, recursively calling, and then all the way we go and go and go until we find the item. If we don't find the item, and the base case is never met, we just return null because there was nothing in this tree and we don't have that item. Finally, the last function is the ToString function, your basic Java function, and it returns the tree formatted as a string, like we did in the binary tree. It uses brackets and parentheses and formats it as parent, comma, data. And for the root, again, we're just gonna, because the root doesn't have a parent, it's just gonna call null, comma, the data of the root. So yeah, this was the binary search tree implementation. Next, we're gonna cover AVL trees, which are with rotations, and there's a little project going with that one.